Welcome to the last session for this conference for today. And so this part, we are going to have three faculty from University of Illinois at Urbana-Champaign to give a presentation. So Max Raginsky is the Associate Professor and William Everett Fellow in the Department of Electrical and Computer Engineering. And Srikant is the Nearing Endowed Professor in ECE. So Niao is the Assistant Professor in the Department of Industrial and Enterprise System Engineering at the University of Illinois at Urbana-Champaign. So they are a team from the Harnessing Data Revolution Tripods program. So they got the award last year for Illinois Institute for Data Science and Dynamical System, in short, IDS2. So along with other faculty, Hugo Chen and Sammy Koyejo, they founded this new institute in 2019 with the support from NSF. So without further ado, I will turn the mic to Max.
All right. Thank you very much, Jane, and the organizers for giving us a chance to present our vision and ongoing work in this institute. So I will talk for about 20 minutes, and then I'll hand the baton over to Niao and Srikant, who will present some parts of the talk. So I will give kind of a broad overview of the institute, and then a brief description of the kind of things that my research group does under this umbrella, and then Niao and Srikant will do the same thing. All right. So as Jane mentioned, this is the Illinois Institute for Data Science and Dynamical Systems, IDS squared. I guess you can think about DS squared, so Data Science and Dynamical Systems. Let's see. Just want to make sure. Okay, here we go. So as it was mentioned, I'm the leading PI, and the co-PIs are Srikant from ECE, Niao from Industrial, Hugo Chen from Statistics, and Sami Koyejo from Computer Science. The first three of us are present today. We also have, let's see, here we go. I just have to keep pressing the mouse to advance. Not very familiar with PowerPoint, as you can see. We have a number of faculty who are also involved with the Institute from both the College of Engineering and the College of Arts and Sciences, representing physics, mathematics, and computer science. And we have two postdoctoral fellows who just joined us this fall. And of course, some of this, we were supposed to have a third postdoctoral fellow, but he is delayed due to COVID-induced uncertainty. So right now he is temporarily working in Amsterdam as a postdoc, but he'll hopefully join us in January. Okay, so the vision of this institute is to essentially synthesize the fields of data science and dynamical systems broadly construed, and that includes fields like control optimization, deterministic and stochastic processes, statistics, things like that. And hopefully, the idea is to grow this into a large-scale event, a large-scale affair that will really showcase the strengths that we have at the University of Illinois in both of these fields. As you can already see from sort of the span of disciplines and departments that the center faculty and postdocs represent. And this, as Jane mentioned, is funded by the National Science Foundation under the HDR Tripods program. So our focus is really on the theoretical foundations of data science using techniques of dynamical systems, again, broadly understood, to sort of facilitate new developments in the field of data science, but also to use data science techniques to build more developments in the field of dynamical systems. So these two sort of sets of disciplines really influence each other in multiple ways, and the goal of this institute is really to explore this and to build these interactions more systematically. And we, of course, are not the first sort of large-scale entity at the University of Illinois that is concerned with such things. Here's a list of some other institutes that really work with problems in various fields, but use techniques from data science and machine learning to do this. For example, Center for Advanced Electronics Through Machine Learning, or CAML, which I'm also a part of, Center for Autonomy. Several faculty at IDS Squared are members of it, Center for Digital Agriculture, and Center for Networked Intelligent Components and Environments, right? So all of these centers really focus on specific domains and use machine learning and data science techniques. IDS Squared is sort of a more theoretical, foundational organization, but we maintain interaction and collaboration with all of these. Okay, so the Institute is broadly organized around 4 themes, representing sort of various primitives or basic questions in the fields of data science. So we talk about data generation and modeling. So how do we represent various complex sources, processes, mechanisms that generate data? Sampling and inference. So this is focused on statistical questions. So for example, how can we obtain high quality samples from various complicated, let's say, spatiotemporal dynamical processes or functional data, things like that. And then 2 algorithms focused themes that they have to do with algorithm design and analysis. So this covers optimization. So whatever optimization aspects of, let's say, sampling or inference are present, this 3rd theme addresses that. And finally, decision making, right? This already enters into the area of control more explicitly, where you interact with some sort of a dynamical system and thus change its behavior by means of your actions. So this covers things like reinforcement learning and related problems of current interest, right? And so we see that both the themes of data, both the strands of data science and dynamical systems really cover this. So this is a chart that really showcases the interdisciplinary expertise among the PIs in the center. So each of the PIs is really an expert on at least 1 or 2 of these themes, and this is what drives the interaction and collaboration among all the faculty, postdocs working with this institute. Okay, and of course, I already mentioned that we are really interested in synergies with existing institutes and entities on campus that use data science in specific domains, and some of the domains include neuroscience, computer vision, robotics and autonomy, genomics, smart cities, healthcare, you name it. All of these application domains obviously rely on advances in data science and machine learning, but also all of these domains are really pervasively coupled to various dynamical systems. Anytime you gather data online with human agents and then use this data to make further decisions, you have a feedback loop, you have a reinforcement learning system, and really carefully understanding all of the interconnected feedback loops and their interaction is one of the goals of the Institute. And obviously using domain expertise is a key component of this. So some activities of this institute, obviously a lot of disruptions happened because of COVID, but we are still plowing ahead. So these are the themes. Research agenda, like I said, involves 4 themes that are really connected to each other fundamentally. For example, data modeling, dynamical systems. Here we're looking at things like functional data analysis, infinite dimensional processes, time series, things like that. That, of course, ties into sampling and inference. So if we want to infer the parameters of a complicated model, how do we do that with statistical and computational guarantees? If we want to obtain samples from some sort of a highly complex statistical model, again, how do we do this with computational statistical guarantees? This feeds into themes 3 and 4, having to do with algorithm design. So once we provide some sort of theoretical guarantees, how can we actually attain these guarantees using given resources, let's say time, energy, data collection, etc., efficiently? And finally, as I mentioned, it's a truism. Anytime you have a data science pipeline that actually interacts with sources of data, people, devices, etc., you have a reinforcement learning system. This is not just machine learning. This is already reinforcement learning that involves, affecting the future in some way. And the fourth theme really explores that aspect. So one of the activities is an ongoing seminar that started in the summer. This seminar takes place every Friday at 2 p.m. via Zoom. And as you can see, we already had a few external speakers, invited speakers, and we'll continue hosting invited speakers, prominent researchers in machine learning, reinforcement learning, optimization, control, mathematical physics. This is just a list of speakers for the fall semester, and we're going to have similar caliber speakers for spring. Well, the workshop plans, we were planning to host a large scale inaugural workshop with invited speakers who were listed on the previous page in this fall semester around the time of the Allerton conference. And obviously, we had to cancel the Allerton conference. I'm actually one of the program co-chairs of the Allerton conference this year, and we've decided to cancel this event altogether due to COVID, because we felt that the in-person interaction of Allerton was such a valuable component of it that that going through the virtual conference, at least this year, seemed suboptimal. But we do plan to have 4 thematic workshops, each sort of focused on one of the 4 themes of the Institute in starting fall 2021. Obviously, I don't think anybody expects any in-person events to happen until fall 2021. Okay, and so obviously educational activities, this is simply a list of various units on campus, courses that are informed by the activities of the Institute. Some of the PIs have already developed courses on, let's say, machine learning, optimization, related things. And so we're continuing to build this curriculum and integrate it with current research that we do, or the kind of things that the Institute focuses on. And obviously the postdoctoral advising is a big component of that in terms of training sort of future generations of researchers. And so our outlook for phase 1 and phase 2 is keep scaling up the capacity, prepare for phase 2 application, meaning that we'll team up with other institutes and put forward the best proposal that we can. Obviously, local collaborations with various application domains, which is already taking place. So a lot of, for example, my current research is motivated in large part by problems in electronics. So that's the as part of the CAMEL on campus. And interestingly, some of the problems in electronics involve really challenging questions in machine learning and optimization and control. But since this is not one of those areas that's considered sort of hot in the popular press, it's not natural language processing or anything like that. There's actually a lot of opportunities to make really fundamental contributions without having a bunch of people with GPUs breathing down your neck or something like that. And obviously, we are developing curricula in data science at both undergraduate and graduate level, seminars, and obviously, we would like to build sort of more sustained partnerships with Research Park and NCSA and related entities on campus. Okay, so this was a broad overview. of IDS squared. And now I and then the other two colleagues, Niao and Srikant, will present sort of a sampling of various research activities. So these parts will be somewhat more technical than this introductory part, but we will try to sort of motivate it and conceptualize things as much as possible. So my own research. So I am an applied probabilist, working sort of at the intersection of machine learning, control, and dynamical systems. And so this was my actually ongoing interest in these two fields before they even sort of took off. And gained this wide popularity. But the idea is that dynamical systems are really pervasive in machine learning. So you start with the fact that most of the data generated by real world sources is somehow dynamic, right? It changes with time, it involves various interactions, causality, you name it. And interestingly, the current paradigm inspired by deep learning is also dynamical. Neural networks themselves are dynamical systems. Definitely recurrent neural nets are dynamical systems, but you can also view the evolution of activations in the neural net as dynamics. And obviously the algorithms that are used to train them are themselves dynamical systems. So therefore one can sort of ask various key questions about these things, such as, well, how rich is the repertoire of systems we can generate, approximate, learn? How is the coupling between the learning algorithm and the system sort of itself understood as a dynamical system and stuff like that? So, like I said, my focus is really on neural nets. Even though a lot of these questions are really classical questions that have been around since about 1960s, 1970s. So one interesting sort of a domain that ties together optimization, machine learning, mathematical physics, and probability is viewing neural networks in what's called a mean field limit. So this is the idealization of very large neural net where you replace the number of the finitely many neurons by a continuum. And I can sort of motivate this in the following way. So if we consider a finite, let's say, two-layer neural net with a large number of hidden units, if you try to approximate a given function using this neural net, you quickly see why there are these fundamental computational issues. If you expand, if you substitute the expression for the neural net into the approximation criterion, you'll see that this approximation criterion depends on the weights of all the neurons, but it's permutation invariant. So if I just renumber the neurons in a unique way, I get the same value. And this already means that the minimizers of this objective are unique to permutation, unique up to a permutation. So that means that there are multiple global minima. So at the very least, we give up convexity, and so there are n factorial permutations for n neurons. So that makes it complicated. So if we pass to this continuum limit, we replace finitely many neurons by an ensemble. And in neuroscience, this is actually a very well-known technique called ensemble or population coding. So you pass to an infinite dimensional description, but what you gain is actually convexity of your objective. Obviously, if you want to pass back to the finite neuron setting, you simply take this distribution over neurons and get IID samples from it. So it's a Monte Carlo type question. So we were interested in the phenomenon where in many cases what happens is you initialize your neurons weights from some distribution like a Gaussian, and then you train this neural net, but the evolution of the weights is microscopic compared to the initial activation, meaning that once you're done training, you look at sort of the histogram of the weights, the distribution, it's very close to the initial one, the Gaussian one, and yet somehow you've minimized your objective. So this can be viewed as an optimization problem on a space of distributions, right? So, and when we are confronted with optimization problems, again, the mean field philosophy says, implement this in continuous time for an idealized infinitely wide network, and then go back to a discrete situation. This is very common in, let's say, models of interacting particle systems through this, you go to the hydrodynamic limit, so you consider everything as a flow, and then you go back to the finite particle limit using sampling, right? So what I have been doing with one of my graduate students, Belinda Tsen, is a stochastic dynamics instantiation of this. Here, the idea is that instead of a static optimization problem, like on the previous slide, where you just find some distribution that balances the representation risk, this L2 error, and the model complexity, this divergence with respect to a prior, you allow the neurons to evolve as independent particles. But then you couple them by means of some sort of an interaction. And this interaction actually somehow averages out when the number of particles increases, and we end up with a highly nonlinear process called the McKean-Vlasov process, which is very common in kinetic theory, theory of multiple interacting particles, definitely computational neuroscience. So here are the pictures of Henry McKean and Anatoly Vlasov, who are the namesakes of these models. So we have characterized this process, and of course, it's an idealization. So our ongoing work is to see how one can implement this in a data-driven, tractable way, because this process involves knowledge of the target function, so it's clearly idealized. But you see the connections between optimization, machine learning, dynamical systems, stochastic control, and mathematical physics already present in this type of problem. And this is the source of a lot of excitement and interaction between multiple fields that really drives the activities of our institute. So I'm going to stop here and hand over the baton to Niao.
So hello everyone, this is Niao, and I'm an assistant professor at the ISC department and also have hold affiliate positions in CSL and EC. So as Max said, I think the four sort of research thrusts of this institute really at the interface of data science and dynamic systems are sort of the data generation, sampling, and algorithm design and decision making. So Max have already given you some ideas of sort of how dynamic systems play an important role in understanding the representation power of neural networks. And I think Srikant is going to give you some more of his work that more in the decision-making aspects of big data systems. And in my talk, I will briefly discuss some of my work, which kind of more focus on the algorithm design aspect of this institute. So I think as Max also pointed out several times, I think optimization really plays a central role in this whole sort of data to decision pipeline and how we can turn data into real decisions. And depending on different appearances of your data, either those are streaming data or distributed data, whether those data are like dynamic or noisy or adversarial, we can always kind of find out a appropriate optimization paradigm or learning paradigm to address the underlying decision-making problem. So I think one topic that's very interesting in this whole line is really how can we develop principled data-driven optimization algorithms in order to make efficient, reliable, and intelligent decisions in the end. So one particular topic I will introduce today is more related to learning under uncertainty and how optimization or dynamic systems play a role here. So we all know that uncertainty penetrates essentially in every corner of machine learning and also in our everyday lives. Nowadays with the pandemic going on, I'm sure everyone has some experience of uncertainty in your own life. So there are many different sources of uncertainty. The most common one is oftentimes the data uncertainty. And most of the, I think, machine learning work is really dedicated to address data uncertainty. And a lot of work are mostly centered at supervised learning or also called stochastic optimization, where we simply model the uncertainty of data as a random variable, and we just want to minimize the expected risk of your model. On the other hand, there are also many other sources of uncertainty like model uncertainty, dynamics uncertainty, adversarial uncertainty, or even task uncertainty. And I think when it comes to these different frameworks, oftentimes the existing research departed for completely different frameworks, like Bayesian. Like oftentimes we use Bayesian approaches to deal with model uncertainty. We use reinforcement learning to deal with dynamics uncertainty. And in practice, also, I think oftentimes we just settled for very efficient heuristics in order to handle extremely large-scale problems. So I think a very interesting question here is really that, can we actually design a unified optimization framework for all of these different aspects of learning under uncertainty so that we can design more efficient and principled algorithms? So in some of our recent work, we find out that in fact, many of these problems as listed here can be unifiedly characterized as this so-called conditional stochastic optimization, which involves a sort of two layer of uncertainties in the objective or in the loss function. More generally, this can also be termed as a minimax stochastic optimization problem, where you have two players, X and Y, that is trying to play this zero-sum game. And both of these problems can be even viewed as special cases of this so-called bi-level stochastic optimization or Stockberger games. And I will just maybe give you just two quick examples to show why these optimization frameworks are relevant to solve these problems and why they are important. So one example is perhaps in reinforcement learning, and we all know that this is kind of one of the driving force behind many of the recent breakthroughs in artificial intelligence. And a fundamental bottleneck that is well known in the theoretical reinforcement learning community is that there is this there is this so-called deadly triad curse of many of the existing reinforcement learning algorithms. Like, it is in general very challenging to integrate both bootstrapping of policy data as well as function approximation, while at the same time to guarantee some convergence. So in fact, most of the existing methods that uses those three aspects oftentimes does not converge in practice. So in our recent work, we've shown that actually this curse can be broken by just simply exploiting this new optimization perspective. So we've shown that we can actually we can just frame this whole policy optimization problem as minimizing this type of mean squared smooth Bellman error objectives, so that we can just directly minimize this and solve it to find the optimal policy and optimal value functions. And this can be further reduced to some min-max problems, which allows us to sort of exploit nonlinear function approximations and also exploit of policy data. And at the same time, we can derive some principled and also theoretical guarantees for this type of algorithms. And we actually also did a lot of experiments on many of the benchmarks Moduco tasks and got much better performance comparing to many of the state-of-art deep reinforcement learning algorithms. So that is one application I'd like to share with you. Another application is really motivated from this macroscopic learning, which basically says in practice, oftentimes we're interested in making predictions at the aggregated level or macroscopic level. Say, for instance, as a world leaders, we're often interested in kind of predicting the total number of COVID-19 cases in United States, or as a university leader, maybe we just focus on the total number of cases at the university level. On the other hand, in practice, there are also a lot of fine-grained informations that are available. Say, for instance, we oftentimes also have access to many of the information at a county level or at a city level. And we also have a lot of detailed data at those kind of micro level. So the idea here is really, can we construct more fine-grained macro models that can be trained, can be learned and aggregated in order to be trained on this macro level data and minimize this loss on the macro level data to make better predictions. And as you can see, that this immediately can be framed as this so-called conditional stochastic optimization, which involves sort of two layers of uncertainties in the objective. so we're trying to actually use this model to make some simple toy predictions on the COVID-19 data set provided by Johns Hopkins. And we used like different, like the kind of the popular SIR model and also a newer ODE models for the macro sort of model. And we trained this only on like 3 months of data set and got quite good performance comparing to methods that naively just use microdata or just use microdata. So basically this example shows you combining macroscopic prediction with some micro information is actually very helpful. So this is just the 2 examples I'm showing to you. And in fact, in a recent line of work, we've shown that like this type of optimization frameworks are also very helpful and can be used to model various other machine learning tasks, such as robust and invariant learning, in model agnostic meta learning, like instrumental variable regression used for causal inference, as well as a lot of those adversarial machine learning applications. All of these sort of optimization frameworks goes beyond the traditional stochastic optimization and shows a lot of potential to build new algorithms and getting state-of-the-art performance in many of these applications. So to sort of summarize, I think the opportunities here, as you can clearly see, that using this type of frameworks helps us to unify many of the existing theory for different subfields of machine learning, and is also fairly flexible in the sense that we can easily extend this type of ideas or these objectives into more complicated application scenarios where you can potentially have multiple or mixture of uncertainties. So if you have uncertainties both from adversarial, from the dynamics of the system, or from the model part, you can always cook up with some similar optimization objective to solve it. And on the other hand, I think another sort of main advantage is that they're very rich of the shelf optimization tools that are readily available that we can actually borrow from and generate some theoretical insights and guidelines of what is a good way to design algorithms and what type of techniques guarantees convergence. So those are kind of the promising side of using this type of frameworks. So there are also some new challenges, I would say, coming with these new optimization frameworks. Like Max was saying that even for minimization problems in the non-convex regime, the landscape can be very complicated. There could be multiple minimal solutions, and there could also be multiple like stationary or even saddle points of those problems. And now if we're moving to a more complicated problem like this conditional stochastic optimization or minimax optimization or even like those multiplayer game problems. So the landscape becomes much more challenging. That means it's much more challenging to design algorithms that guarantees convergence, and it's also much harder to analyze what are the behaviors and stabilities of different algorithms. And so these are based, and to answer all of these questions, I would say that dynamic systems play the most important role here, because really that all of those gradient-based methods that we're thinking about can be viewed essentially as discrete time dynamic systems. And using the existing theories or new theories on dynamic systems helps us to really understand when does an algorithm converge, where does it converge to, and how fast it will converge. And I think all of those are kind of currently ongoing work with the group and also the students and postdocs in the group. I'm happy to talk more in details by the end of this session. Yeah, thank you. I'll just turn it to Srikant then.
Thank you, Niao. So I will summarize the activities that I've been involved as part of our institute. I'm Srikant. I'm a professor in ECE, CSL, and affiliated with computer science. And I'm also the co-director of a relatively new institute called C3.ai Digital Transformation Institute. So some of you here may be interested in a workshop that C3.ai DTI has organized this week on deep learning theory. Okay, so if you think about big data systems, people are collecting massive amounts of data. So this is even from a year or two ago this is a slide that I used maybe a year and a half ago or something. So Facebook at that time was generating 4 petabytes of data per day. Massive numbers of servers. Google's data centers had at that time 2.5 million servers. And this data is used to solve really complex, large-scale state and action space problems, which have great impact on society. For example, autonomous driving. I mean, I don't necessarily mean self-driving, but I mean electric cars have all kinds of assist capabilities to help the driver to drive in difficult circumstances, for example. And so big data systems sort of span this thing from data collection to data-driven decision making. And I'm primarily interested in 3 areas. So one is neural networks, how to train neural networks for specific tasks and how to understand the fundamental limits of training and generalization. In cloud computing and data centers. So these machine learning workloads, for example, training a neural network. So this is done in a data center consisting of lots and lots of servers. And a very interesting and challenging question is that if there are many, many servers available to schedule your workload on, which server should you schedule your workload on? And finally, on reinforcement learning, and I think Niao touched upon it a little bit, which is designing algorithms and understanding the fundamental limits of training and online decision making using either neural network-based reinforcement learning algorithms or just reinforcement learning more broadly. So I'm just going to give you a small sampling or a quick sampling of my results. They all have a common theme, and hopefully I'll just briefly touch upon the common theme, even though these look like disparate problems, they have a common theme. So here's an example of what is called over-parameterization in neural networks. So here are some examples of neural networks. So these are all sort of, let me pull up a pointer. So these are examples of, caricatures of neural network, how the shape of the neural network, if visualized, will look like. So these are 4 examples of 4 neural networks that are very popular and have and are known to work very well on difficult data sets. So if you look at these 4 neural networks, all of them have been trained on the same data set called ImageNet, which has 14 million images. And these neural networks, on the other hand, have far larger number of parameters than the number of images on which they're trained. So VGG16, for example, has 138.4 million parameters. I mean, so this is massive compared to the number of images that you're training it on, which is weird even for those of you who don't know much about neural networks or machine learning. I mean, I'm sure all of you here know about machine learning, but if you don't know about over-parameterization in particular, I mean, I'm sure all of us have done physics experiments in high school where you try to find the spring constant by adding masses to a spring and figuring out how much displacement there is for each weight that you add. And you get a lot of points, and you don't try to draw a very high order curve through those points. You try to draw a straight line, right? I mean, the reason is that you don't want to overfit, because now if you're given a new weight, then you don't, to predict how much displacement you're going to have is going to be difficult. So it's been ingrained in us that you need to use a small number of parameters. But interestingly, modern neural networks work by using a number of parameters that are far larger than the number of data points that are used to train them. And so it's somewhat mysterious and interesting to try to understand why this works. And one of our recent results is that suppose you're given a data set consisting of n points, and you have a neural network with just n plus 1 neurons, 1 neuron more than the number of data points. It is possible to design an algorithm that fits the data points reasonably well, but more importantly, generalizes well. So here it's an over-parameterized neural network. So there's more neurons than the number of data points, and each neuron has actually multiple parameters. So the number of parameters we need is larger actually than n. And what we show is that despite this, you can find a nice algorithm. So over-parameterization sometimes can help in optimization questions like the type Max and Niao talked about. And in designing, training a neural network is essentially an optimization problem. And having more parameters can actually help with the landscape of the function you're training or the function you're using to train. But despite that, the neural network generalizes well. And so in this recent paper, which we are still actually in the process of writing it up and putting it up on arXiv, we are able to show why this works well. Another type of result, this is not quite exactly machine learning, but this is on data centers and cloud computing platforms that are used to train machine learning algorithms. So data centers consist of millions of servers, and the goal is to design scalable algorithms so that when you send a machine learning workload to a computer, you want practically zero waiting time. You want the answer to come back as fast as, the only time you are willing to wait is how long it takes for the machine learning algorithm to execute. Whereas typically in a data center, there are multiple jobs, and if a server is handling one job, then it has to wait for the next job you have to wait for that job to process before you're able to execute the next job. So the question is, can you achieve this with zero waiting time? And it was an interesting example that one of my students gave me who interned at Amazon Berkeley. So for example, when you go to Amazon and type something, there is a machine learning algorithm which decides what you need to see on your screen. I mean, in addition to whatever you searched on, it also shows you other things and so on. And there's a machine learning algorithm that's at the back end of this that does this. But we see the results practically instantaneously. And how does this work? So traditionally, people have been studying this problem in the following manner. So you have a massive data center consisting of thousands, if not hundreds of thousands or millions of computers, and you have to decide which computer you want to, or server which you want to send your job to, your machine learning task to. So much of the theoretical work in this area, at least has assumed that the problem is because of the size of the data center. It's just simply so large, and you have to decide, which computer to send your job to. And the challenge there is because there are so many servers, it's hard to figure out. If there are a million servers, you can't examine all of them and figure out how many jobs are waiting on each one of them. And then the goal was to figure out how to do this in a low complexity manner, examine just a few of the servers, but still get good performance. But there is an additional wrinkle on this. In actually most modern data centers, you cannot send your job to any server that you want. You can only send your job to the servers that have the data that you want to that you need to execute. So one example would be, suppose you're trying to figure out how many occurrences of the term presidential election were in news stories on CNN yesterday. This, you can only send it to those servers that are storing news stories from CNN from yesterday. I mean, you can't send it to any server because some servers may not have this data. And there are other examples in the context of Amazon, squaring, and so on. And one of our recent results is that there is a very simple low complexity algorithm called join the fastest of the idle queue. So basically, you look at the subset of servers to which you can send data, and look at how many of them are idle, and then you basically send it to the fastest of those servers. And if nobody's idle, then you just randomly send it to one of those servers. And what we show is that under reasonable conditions, if the data center network is reasonably well connected, but reasonably well connected means it's actually relatively sparsely connected, sort of like for those of you who know Rayadurgam type of graphs. I mean, it roughly requires the same type of connectivity that is required for a graph to be fully connected. And you can show that this algorithm achieves zero waiting time. So this is a recent result that we got with a undergrad student from Tsinghua who was visiting me earlier this year. So the third result that I want to talk about is in the context of reinforcement learning. Most of you probably know what reinforcement learning means. So you have an agent, and the agent takes an action. The action that you take, for example, if you're a self-driving car or autonomous driving system, you decide to accelerate, decelerate, change lanes, and that changes your relative position, which is the state of the system at the next time instant. And this relative position, you have sensors like neural networks, you have radars, lidars, cameras, which are interpreted by a neural network, and you get feedback saying the state of your system, which is basically your relative position with respect to other cars in the network has changed, and the system has changed. And then based on this, you again take another action, and you might get some reward or cost for doing this. For example, if you get too close to another car, then of course there's a cost associated with it. Or for example, if you're trying to merge onto an exit, and if you manage to do it quickly, then you get a reward for it. And so reinforcement learning tries to do this by taking into account your state and what your action does to change your state. And this has, of course, been widely used in video games, board games, and in the context of autonomous driving in electric car companies. And I've been interacting with one of them over the course of the last year, and I'll talk about that in the next slide. So there are two results here. One is a finite time and asymptotic performance bounds for well-known reinforcement learning algorithms. So for example, you might be interested in the following question. How long should I run my algorithm? Meaning that how many samples of data do I need for my algorithm to achieve some degree of accuracy? So we have a paper, we had a sequence of papers from Colt last year to NeurIPS and NeurIPS this year again on trying to understand answers to questions like this. But somewhat more interestingly to a broad audience, I've also been working with a electric car company, and where we are trying to beat or improve the automated lane merging algorithm that they have. So the goal of this algorithm is to merge onto a highway. And currently they use a algorithm, which for those of you in the control area might know, call it a model predictive control. They have a fancy name for it inside in the car, electric car industry. So that algorithm has a certain performance, but the performance is measured in terms of three things. One is multiple things, actually. One is the comfort of the driver, which is measured in terms of the derivative of the acceleration called jerk. The other metric they use is how long does it take for you to merge onto the highway. What is the third metric? And then there are other constraints, safety constraints, such that you cannot get too close to the car on the highway that you're merging onto. And you have to maintain speed limits and so on. So they use model predictive control, and they have an algorithm. But the interesting thing is that if you use reinforcement learning to train a car to do this, it actually performs well on both the comfort level and how quickly it merges. But on the other hand, it crashes more. Clearly you want to live when you're merging onto the highway. So it's not good even if the crash rate is a bit higher. So what we've been working is, can we sort of take the benefits of both MPC? So can you get an algorithm that actually has nearly as good a performance as reinforcement learning in terms of comfort level and how quickly you merge onto the highway, while maintaining the safety standards that the MPC algorithm has? And we have some interesting results lately on this. So the common theme in all of this work is that we like to model all of these things as dynamical systems. So there is a state of the system, as I mentioned in the autonomous driving scenario. It is your relative position with respect to other cars in your neighborhood, and your position is of course controlled by something. So by applying some kind of acceleration to your car. And there is random noise, which is basically the behavior of the drivers around you, for example. Okay. And my favorite technique, so the slide is a little, some equations in it, but I will wrap up soon. So my favorite technique, for those of you interested in this, is to basically, very, very simple idea. Suppose you have a stochastic process that is in steady state. Then if you take any function of the stochastic, the state of the stochastic process, it doesn't change from expected value, doesn't change from time to time. Now, if you do if you take the left-hand side and sort of approximate it by the derivative multiplied by xk plus 1 minus xk, which is the change in the state, plus some, of course, this is not exactly the derivative, so there will be some additional term here. And there are clever ways in which you can choose this function v, which I call the Lyapunov function, such that the first term is approximately equal to the expected value of some performance metric that you're interested in, and in such a manner that then you can get a bound on this g. Okay, so the question is how to find v, and then how to get bounds on this expected value of g, and there is one technique. So actually, I originally sort of started developing this thing called state space collapse. State space collapse is an idea that's been used by probabilists for a while, but in our work, we've been using a new definition of it and a much more accessible way to look at this for the last 10 years or so, I've been working on this. The basic idea is that if you can prove that the original high-dimensional system lives near a low-dimensional space, then it's easy to construct a Lyapunov function in the low-dimensional space and sort of somehow figure out a way to use it in the high-dimensional space. That's one idea. But lately, I've realized that actually this idea is very closely connected to something called Stein's method, which is an idea used in mathematical statistics to prove the central limit theorem, for example. And Stein's original idea was sort of further developed by Barber, who showed that this is very closely related to how two Markov processes are close in terms of their generators. So what he showed is that Stein's method is closely related to this idea that if the generator of two Markov processes are close, then the stationary distributions must be close, and that idea can be used to design Lyapunov functions. I won't get into it more, but just in case there are people here who are interested in this kind of stuff. So one interesting theoretical thing that I've been very interested in is try to understand how to design a Lyapunov function such that just setting this thing equal to 0 simply gives you an answer to whatever metric of interest that you're interested in studying. This has proved to be a very successful method for me over many years now, and I'm now sort of exploring connections to Stein's method and other ways of coupling the generators of two Markov processes, and it has some interesting, as I mentioned, so we've gotten some interesting results out of this technique for multiple different problems in the machine learning / data science space. So that's it. That's the end of my talk.
Okay, thanks a lot for the great talk. So any questions from the audience? You can raise your hand and I can just unmute you, or you can just unmute yourself. Oh, yeah, Ilya.
Thanks a lot for joining us and talk about your project. Let me just try to set a tone for the comments that we want to share with you. And this morning we had a presentation about the goal of having a day dedicated to hear from people like you that are leading Harnessing the Data Revolution projects. And the idea is, as you will know, NSF is in the process of compacting some of these ideas. 40 plus projects have been funded, and only 5 to 7 of them will converge into an HDR institute. And so, following the suggestions from Amy Walton, we are trying to create synergies with projects like yours to go and try to compete for one of these institutes, right? And so something that we heard from NSF is that the things that we are doing at the intersection of AI, innovative computing for some physics and astronomy projects could benefit greatly if we, for example, go and join forces with geosciences. And we had talks from Paul Morin, Zhao, and Wang, and others this morning and afternoon about that. And they are enthusiastic about creating synergies, convergence with us. And so the goal of having you here is to also explore whether there is a potential opportunity here to catalyze the activities that you are doing for algorithmic design, for innovative computing, for some of the problems that we are also trying to address. So we would like to hear your opinion on this.
So you said the application area is physics, is that right? Physics and what else?
So we have, in terms of, to give you a better understanding, we have applications in multi-messenger astrophysics. Basically, we have a lot of complicated data sets. These are fast data sets. These are complex, heterogeneous, you name it. And they come from multiple detectors, images, time series. And then there is the other end for high energy physics, and Phil can tell you about the problems that they are facing. And so the goal here is for these disparate data sets, big volumes, high speed, etc. Is there any chance to apply foundational approaches beyond what we are doing right now, which is GPU accelerated computing, FPGA, high performance computing, etc.? Is there an opportunity here to harness what you're developing, what you describe in your presentations, to bring in these novel ideas into the work that we are also producing.
I guess we'll have to think about it and understand the problem a little better.
Yeah, I mean, the two of the co-PIs, Hugo Chen and Sami Koenjo, I mean, they are closer to more of statistical and applied computational side of things, and both of them work with all sorts of functional data, spatiotemporal processes, etc. So this is something that I think the institute expertise can cover, but
Hugo was on the call, by the way.
Oh, that's right. Yes.
So Hugo, do you have any comment?
Yeah, right. Yeah, so actually, I have been involved in some project related to this space weather. They use heat micro models to use data simulation to study, based on this satellite image, to study the solar corona, like to predict like corona mass ejection or some other space weather. So, so there's a potential. I think that the object you mentioned in the astrophysics, they could be like dynamic objects rotating or moving around. And based on these different observations you have, you might want to retrieve what is going on in this 3D object. So I think there's a potential connection with what you have been talking about. Right.
And maybe just to add more context to it, maybe Phil, you can give them a crisp overview, or what are the challenges that you face in high energy physics?
Yeah, so I mean, so like in the last talk, right, you talked about like Facebook doing 4 petabytes per day of data and trying to use that. Our data rates before we, let's say, we save a little bit less than 4 petabytes per day. It's like maybe 1 or 2 at the moment, but we actually process, we actually filter that down already by 8 orders of magnitude. So the amount of data we start with is like, it's like a petabyte per second. And so actually in kind of the middle tier, we start where we process data at, let's say, it's about 10,000 times. So 10,000 times a petabyte per day. At that rate, we start to use kind of heterogeneous computing to process the data. Our problems, we have very good simulation and kind of established reconstruction techniques. So a lot of our problems have like good machine learning solutions already. So a lot of it is really exploiting heterogeneous computing better. And then a lot of it is also, well, a lot of it is also, since we have kind of conventional algorithms, a lot of it is also coming up with like machine learning algorithms that can outperform our conventional algorithms. And our data sets are often quite complicated. They're not just like images, right? They're often can be, let's say, a sparse pixel array with, not just, position and time, but also with energy, other additional properties, particle type, et cetera, et cetera. And so there's rather complex, the data set's rather complex. And the nice thing is it's a very controlled environment. And we have very good simulation. So it's naturally, using machine learning has been a well-established thing in our field. And kind of our big strategy now is, can we increase our throughput and process data, with higher quality faster? And there are many orders of magnitude here that we can, the faster you go, the more we can, process data, and the more we can find potentially, hidden signatures like dark matter and so on.
Very interesting. So I guess you approach it from 2 different angles. One is sort of improving the computational infrastructure to make things faster, and the other is to sort of come up with algorithms which run faster or give you results sort of coarsely first, maybe, and then maybe refine it quickly. Yeah. Okay. I vaguely remember talking to Katie Bowman. I gave a talk at Caltech last year, and I noticed that she was a speaker on the first day of this conference. I think she has been talking to. I did remember talking to her about something, and now I don't remember what it was, but I think she has been working with some machine learning people at Caltech on multiple types of problems, and there are people like that here too, like Max suggested. Sammy and Hugo, who's here. Yeah.
And let me just say that for the bridges that we are building, the Event Horizon Telescope will be part of that institute idea.
Okay.
So if you want to see like the high-level vision, we have high-energy physics, multi-messenger astrophysics, event horizon telescope, and geosciences. And all of them look quite disparate, but actually they are threaded by the same problem, which is high-dimensional data sets, big data sets, we need to accelerate throughput, etc. And so we have like the building blocks for the domain areas. Now we want to strengthen the AI expertise for such an institute. And one thing that you mentioned, Srikant, related to the high dimensionality of the data, that's a problem that we have in multi-messenger astrophysics. The main challenge, as opposed to high energy physics, is not the data volume. I mean, you have many telescopes, yes, you have a lot of data. But for the type of sources that we are exploring, for example, LIGO just broadcast about a few megabytes per second. So it is lightweight, but the dimension of the parameter space is 15-dimensional. And so when you need to go and sample this parameter space to search for signals, that's a big challenge. And so when you were talking about, is it possible to reduce the dimensionality to something more manageable, that's something that would be very interesting to explore. And another thing is forecasting. How can you predict that in several minutes or in a few seconds, there will be an event that will produce gravitational waves, electromagnetic waves, etc. Can you give this information ahead of time to people that have access to telescopes to find these sources? So there you have interesting applications, right? In terms of also predicting patterns as you find in Amazon data or in Google, etc. for the stock market.
I guess people in signal processing here could also, Jane would probably know better. I mean, lots of people who work on dimensionality reduction. I mean, that's a significant part of signal processing, right, Jane? So there are people, I mean, you.
Yeah, so I'm part of the team working on some of the denoising and also parameter estimation problems. So we are not yet into this 15-dimensional space yet. We are still relatively working on the like low-dimensional parameter space. So what I think Ilya was talking about is the intrinsic parameter space is actually very high-dimensional. It's not the signal itself. The signal itself is very long, like 1 second. They sample at 8,192 kilohertz or yeah. So actually, when you look at the data set itself, if you just represent 1 second long data, it's actually already very high dimensional. But I think the key problem is actually inferring the parameter in this intrinsically high, relatively high dimensional parameter space.
And so the problems that I've worked on for dimensionality reduction is more using control, actually. You use a control action to reduce the dimension of you make a system that's large dimensional appear. I mean, like just simple example would be supermarket. You go to a supermarket and let's say there are 10 lanes. Automatically people find the shortest of the 10 queues, right? And then so which basically means that if you join the shortest of the 10 queues, then roughly all 10 queues will have the same length most of the time, which means if you know the length of one queue, then you know the length of all the other 9 queues. So basically you have dimensionality reduction by devising a clever algorithm. Of course, humans do it automatically, but the question is, can you do this in a data center so that you have a very large dimensional data center with lots of computers appearing, so it's a very, very small data center to you. And then you can design algorithms and analyze it and understand it. So control is sort of central to what I do. But I think signal processing people probably are, more adapted, sort of looking just purely at the signal without any control and seeing what dimensions,
But I think that is very relevant to the real-time prediction. Like if you want to have a big data center for the real-time event, probably what you talked about for this data center or cloud computing is going to be useful.
Okay.
Yeah, I mean, a big component of our work is just taking an algorithm and then shrinking it. Right. So for example, if you know Song, he's part of our institute, Song Han at MIT, and his specialty is just taking the same network, shrinking it down by an order of magnitude, and having it, it perform ostensibly the same. Right. So if there are ways to have algorithms which were originally very large, perform on a have the same performance or or marginally smaller performance, marginally worse performance, right? But have much lower like footprint, right, in the data center. That's a huge gain for us, right? Because then we can use our computing much better.
All right.
Okay. Thank you, everybody. Bye.
Thank you.